Okay, so final exam review. Here are the questions of interest. Let's start by focusing on this. So I think this is something that maybe have been an announcement to you guys or something, but, oh, really? Oh, well. This is like a nice place to start. Truthfully, like, this is basically all the key points we hit. And they told me, like, when we're talking about what we want to focus on, we're going to cover the most important stuff from the first 2/3 of the class. So that's reflected by this list. And then we're going to have each main topic after midterm 2. And again, that's basically reflected in this list. So I think what's helpful here is to kind of see like what's excluded, which is like those, let me see here. Those power loss and transmission lines. Someone emailed me about that. Don't worry about that. The bore. I'm sorry? What? Okay. And then secondly, the don't worry about the Bohr atom thing either. Okay. So this is a nice place to start. Like I said, it's basically the main things, like the big highlights from the first 2 stuff and all stuff we're going to focus on in the worksheet. And then basically all the other big key points that follow midterm 2. The last thing is, I know like between the 2 classes, there's some like points that are going different ways and there's a lot of factors to consider. The professors are going to account for that once they finish the class. And physics itself is pretty chill about those things. So you can like reach out to them and stuff. And it's hard to reach them sometimes. If you can't reach them, email me because they'll come back to me quickly. So don't wait too long. Just email me and I'll help you out. Okay. Oh, and then the last thing is if you guys have homework or exam questions, you can't email me and be like, how do I solve this? Or where did I go wrong? Because this takes me too much time to go through everyone's 8 questions and like figure out where you went wrong. But you can ask me a specific question and I'll email you back in 2 seconds. Okay, let's roll. So let's focus. Let me just pin my video. So, okay. Question 1, this stuff should look pretty familiar at this point. So here we have this 2-point charges. They're assigned to these positions along the x-axis, and we want to determine the net electric field, that's both magnitude and direction, at point P. Okay, so we're dealing with this kind of like vector addition, and like I said, this would be something that should look pretty familiar. So Q1, point P, here. Yeah. Okay. And we want to find the net electric field at point P. So let's just start by assigning our vector direction. So we have a positive acting at point P, a test charge, which we're going to say is, we assume is the positive, right? So that means it's going to repel. E1 is going to point this way. And then that test charge with respect to Q2, excuse me, is a negative. So it's going to be attracting there. So it's going to be attracted to Q2. And we'll call that E2 like this. Okay. So we set up our vectors. The next thing we need to do is calculate the distance between the charge and our point of interest. So we basically have a line here. We'll call this R1 and another one right here. And we'll call this R2. Okay, so R1, they tell us is equal to 6 meters. R2, we can calculate using Pythag. Oh my gosh, it's like some grad photos happening right outside. Equals 6.32 meters. Okay. And the final thing we want to do is find our components. So we have a standard X and Y coordinate system. Carlos, I haven't seen you in a while. Yeah. We have our standard X and Y coordinate system, and we're going to break down E2 into its components. So the angle theta is going to be right here. We'll say this right here is going to be E2. E2 vector is touching the angle theta. So we'll say cosine theta. And then we're going to have the X component E2 opposite the angle theta, so sine theta. And then we'll be able to solve for E net, because our E net equation is going to be Okay, and let's first solve for E net X. So we look at everything in the X direction. Anybody, what should I plug in? Anybody want to just tell me? There's one vector in the X direction. Exactly, E2 sine theta. Okay, and the next thing, we're gonna have to use our equation for the electric field of a point charge. That's gonna be equal to K. The charge here, we're talking about Q2, divided by the distance between them, we'll call that R2, and and then sine theta. Okay, so now you just got to work this out. You get 213.71 newtons per coulomb. And then next we're going to solve for E net Y. E net Y. Is the sun in your face? Can you mind pulling the one that makes it shut? It's the one that is not like looped. And then E net Y, that's going to be equal to E1 going in the positive direction, going upwards, minus E2 cosine theta. Okay. And now we can just plug in again. So KQ1, the distance between them is R1, minus KQ2, the distance between them is R2 cosine theta. Oops, cosine theta. All right. We now have to plug everything in. I recommend you factor K out, just kind of save you time plugging stuff in, and you'll get minus 391.3 newtons per coulomb. Okay, that's E net Y. So now we need to solve for the total sum of the electric field. So we're going to draw another a vector here, or do another vector addition. So we have E net X is positive 213. So therefore, it agrees in the direction we defined as positive, which was going rightwards. So we're going to say this is going to be E net X. And then E net Y came out as a negative. Therefore, it's going to be pointing downwards because we said positive was going up. So E net Y. Okay, you're going to combine these guys. We're going to have our angle theta prime here, and this is going to be equal to E net. I already told you how to solve for E net up here, so just plug in everything in. E net comes out to be 445.5 newtons per coulomb. Solve for the angle. You can just run a tan function opposite over adjacent. That'll be your y, E net y over E net x. Theta prime is equal to 61.36 degrees below the positive x-axis. Okay, kind of went fast there just because this one should be major review and I want to focus on the newer stuff. Okay, so there's that. I saw a chat question. Let me pause real quick. Okay, question 2. This one should look familiar from before, just because I want to make sure we don't forget it in a question that could come up. So question 2, for the configuration of charge shown in the first question, we want to determine the net electric potential at point P, and that's going to be question 2, and we'll call that part A. So what are we solving for? We're solving for the net electric potential. So what's net electric potential? That's the voltage of a point charge, which is going to be equal to KQ over R, right? So we're going to have our triangle again. I'm just going to kind of draw it rather quick. Is point P, okay. Such, and we're solving for the electric potential at that point P. So I'll say what we're looking for is VP. What's that equal to? We will soon find out. We already know what R1 and R2 are equal to. We found that before. And to solve for the potential at P, it's going to be the sum of V1 plus V2. Okay, so this kind of underlies the point that voltage is a scalar. And therefore, as a scalar, when the charge is negative, you plug in the negative, right? There's no vector to tell you which way is going which way is positive, which way is negative. If you're a scalar, you plug in the negative, which it tells you. So in this case, we know Q2 is negative. So when we write this expression out, Q1 over R1 plus KQ2 over R2, make sure when you plug in Q2, that you recognize that's going to be a negative there. Solve for VP. VP is equal to minus 2772.15 V. Okay. And then finally, the to calculate the total electric potential of the three charges. This question was on my final when I took the class, and it's just like an equation that sometimes people forget, and I'd rather you have been exposed and not need it than the other way around. So essentially what you're looking for is we have a third charge placed at point P. Oh, and I forgot to correct this. That third charge has a value, so Q3 is going to be equal to -5 microcoulomb, okay? What we're asked to solve for is the total electric potential energy of these system of charges. When you see those words, total electric potential energy, that's that U total is what we're going to be solving for, right? We don't know what that is. We see system of charges, you should be thinking in that realm. So we'll draw our triangle again. Okay. Here now we have Q3, which is equal to -5 microcoulomb. Here we have Q2, which is equal to -3 microcoulomb. And here we have Q1, which is equal to 1 microcoulomb. We already know the distances between all these guys. That's going to be equal to 6.3. Call that R actually, 6.32 meters. I'll call this Y is equal to 6 meters, and I'll call this X, which is equal to 2 meters. Okay. Now, with these kind of questions, essentially what you need to do is calculate each combination that exists between them. So you need to calculate the potential between 1 and 2, between 1 and 3, and then between 1 and 2. In this case, there's 3 combinations, but you can see that as you add a charge, the number of combinations will start jumping up a lot faster, right? So to calculate the number of combinations, all you have to do is take the equation n, let me do this in white, n parentheses n plus 1 over 2, where n is equal to the number of charges minus 1. So in this case, we have 3 minus 1 equals 2. Plug in 2 for everything. You'll come out and for 3 combinations. 3 combinations. Q1 with Q2, Q1 and Q3, Q2 and Q3. Those are your 3. So then U total will be equal to K Q1, Q2 over the distance between them, which is X, plus K Q1, oh, out of space, Q3 plus the distance, or divided by the distance between them, which was Y, and then plus K Q2, Q3, the distance between them, which is R. Okay, and you're gonna, again, you need to plug in the sign of these guys because this is going to be a scalar value. So, and also in this scenario, I recommend you factor out K because this can become kind of intensive on plugging in. Solve for U total. You guys know how to do that. It's going to be 0.000361 J joules. Okay. And also, whenever I put a bracket over zeros, that means there's 3 zeros. So sometimes my writing's kind of bad, but when you see a bracket, that means that's a group of 3. All right, let me pause real quick. So a question is like, when can I use loops? When should I use Kirchhoffs? And without I'm not going to even go there. When to use Kirchhoffs? Well, there's kind of 2 scenarios. Either when you have batteries in parallel, as we have here, or when you have capacitors and resistors in the same circuit. So either of those 2 things, that tips you off. Time to do Kirchhoffs, time to do some kind of loops. Because when you use a loop, you can solve for a lot of stuff because there's like these consistent laws given by the junction and the loop rules. Okay, so whenever I start one of these, and I know I do this a little bit of a different way than they teach you in class, but I think my way is a lot faster and easier to understand. So we're going to label our junctions first. So we're going to have A and B, as I like to call them. And next, I'm going to label my currents. So some of you guys know the trick I like to do when I talk about the direction of my currents. And basically, it doesn't make a difference, but it can be right most of the time. So it's kind of nice. So what I do is I look for the battery that is the strongest battery, the biggest battery. And I assign the direction of current through it as if like the true direction of current, right? So, you know, normally this is the minus terminal and this is the plus terminal. So then you would expect the current to be going that way, right? And then I look at the next one. I look at the next highest one. That's that 18 volt right here. And then let me call this I1 too. Red is I1. I look at the next biggest one, 18 volts, and I assign the direction of current like the same, the way it would truly go. And that's I2. Okay. And then I look at the smallest one and, oh, well, fortunately for me, in this case, it actually works the intended way where it's going to be going from minus to plus terminal, where what goes in equals what goes out. But had it been something in this case right here, and it's 2 volts, I'm like, okay, it could overpower it and go that way. And then when you do it that way, your values normally come out positive at the end, but it's not for sure, but it's how I like to think about it. Okay, but like I said, in this case, things worked out nicely, and it actually does go this way. Okay, and now we can write our first junction thing. So the junction our junction rule is what goes in has to equal what goes out. So what do I have going in? I have I1 going into A. I have I2 going into A, and what goes out is equal to I3. I3. Okay. Next thing, my loop equation. So loop L, and I'm going to do this loop right here. I'm going to do a loop in this one, and I'm going to do a loop around because you need to have the same, say the same, at least one of the same currents in the same one, right? Or in both equations. And how I like to assign the direction my loop will go is I look for the strongest battery. In this case, that's 20. I then draw the loop and as if it's going through the battery the way the current will, right? So such that the current, gosh, why can't I draw this? There we go. Such that the current and the loop are pointing in the same direction, right? Remember, this is the big battery. So I1's going this way, and this is the big battery. My I2 is going to be pointing that same way. That's how I like to set it up. And that's done deliberately because, with our loop, we set everything equal to 0. And I start behind the biggest battery, which is equal to 20. So now I know that my battery is going to be equal to a positive value because 20 is bigger than 18. So we'll subtract it 2. Okay. So then, I forgot to label my resistors. Excuse me. Okay. So now I move on to that first resistor, that 5 ohm resistor. Because the loop and the direction of current are pointing in the same directions, I write minus 5I1, okay? Loop and current are in the same direction, minus. I then tiptoe my way around, keep working. I now hit this resistor 3, okay? Now my direction of my loop, which is going this way, and the direction of current, they're butting heads, right? They're bumping into each other. And because they bump into each other, that's plus 3I2, okay? And then I continue working along, and I hit this battery. Because I hit the positive terminal first, and then I go to the minus, right? My loop goes like this. First, it hits the positive terminal. That becomes minus 18, right? So I hope you can appreciate the difference, which is down here, we went minus terminal to plus terminal, right? That was a positive. And up here, we hit positive terminal first, and then minus, that's negative. Similarly, here we have our loop going this way. It's in the same direction as current through this resistor, therefore subtraction. And then up here, our loop is going the opposite way of the current through this resistor, therefore addition. Okay, and I'm not going to explain that now every single time, but that's how I'm doing this. So clean up this equation, and what I like to do is get one, namely the current who has a smaller value. I divide everything by that one, right? So such that it's a little bit cleaner of an expression. So 0, after you 20 minus 18, 2, divide everything by 3, you get 2 over 3 minus 1.67 I1 plus I2. Okay? Now my second loop. I said I'm going to use a nice big guy out here. Call this loop 2. Going in the same direction as loop 1. Okay? So what do I like to do? I start behind my biggest battery. Loop direction and current direction going through that, I should say, the loop is going from minus to plus terminal through that battery. That's going to be 20 volts. Okay. Go down to the first 5 ohm resistor minus 5I1. Go to the 2 ohm. That's going to be minus 2I3. And then we're going to go to the battery, which is going to go minus plus terminal, so plus 2. Okay. Clean this up. I'm going to divide everything by 2. And I'll end up with okay. And now let's adjust my junction equation. We have everything on one side. So minus I3 equals 0. Okay. And now let's solve for what I2 and I3 are equal to, such that we can solve for everything in terms of I1. So nice and easy, solving for I3, just move it to the other side, 11 minus 2.5 I1. Okay. And then I2, it's going to take a little bit of working out, but I2 is going to be equal to 1.67 I1 minus 2 over 3. Okay, so notice what I did here was I had both equations had I1, and that's reflected in the fact that both of my loops are going to be dealing with this I1 portion right here. You have to keep I1 on this side of the equation, right? Otherwise you can't solve. So you're going to have to solve for I1 and I2. And now we can just plug in I1 and I2 into this cleaned up equation. So I2 here and I3 here. So let's write that out. So therefore, I1 is equal to 1.67. Oops. Oh gosh, what am I doing? That should be a plus. So I1 plus 1.67 I1 minus 2 over 3 minus 11 plus 2.5 I1 is equal to 0. Clean this up, solve for I1. I1 is equal to 2.26 amps. Okay. And that's why I like to have these guys right here, because now all I need to do is plug in I1, and I can solve for I2 and I3. I2 is going to be equal to 3.11 amps. And then I3 is going to be equal to 5.35 amps. Okay. And let's go over a case that didn't happen, but let's say one of our current values comes out to be minus, so let's say this is the fake one now, I2 equals minus 5 amps, okay? That's fine. That doesn't mean you solved everything wrong, but I would say that, okay, that came out negative. That means my guess on the direction that the current was going, which was, it was moving westward in this diagram, was wrong. So I would say, therefore, guess was wrong. I2 goes eastward, right? Yeah, eastward, and I2 is equal to 5 amps. Okay, so that's just something in case your guess comes out wrong. But that's why I like to do my little trick where I start with the biggest one, assign the current, because normally that way it can kind of work out nicely, but it's not surefire. So yeah. So this is the we want to find equivalent capacitance, and then we're going to determine the charge on each capacitor when they're connected to that 12-volt battery. Okay, so it's always kind of hard, like, where do I start these kind of questions? Typically, the rule is work farthest away from the battery and then work towards the battery. But we're pros now. So if you have a really good eye, you can see that the first thing you can do is hit these two in parallel, right? Because they're not talking to each other. They're both separate and they're both in parallel. So you can set up a situation where we have P, and I'm going to say P prime. So how do we condense capacitors that are in parallel? Yeah, you just add them up. So then CP prime is going to be equal to C5 plus C6. And that's going to be equal to 10 microfarad. And then 4 plus 4 plus 2 is also equal to 10. So that's CP is going to be equal to 10 microfarad. Okay. And remember, I like to put these in quotes. And that's to remind me when I'm working backwards that capacitor really doesn't exist, but it's the result of a condensation of them. So when I redraw this, it's going to look something like this. Let's see. Oh, C1. Okay, C1, and this is 12. Okay, so this is what I mean when I put in quotes. These capacitors they're not truly there, but they're what we got from a condensation. And when we work backwards, that's a nice way to remind me that that within this capacitor exists these three, and within this one exists those two. Okay, so these guys are in series. Clean it up one more time, and that's going to be your equivalent capacitance. And when you solve it, you just do that reciprocal addition. So the final is going to look like this, and then it's going to be equal to series 2.5, which is also equal to CEQ, and that's going to be 2.5 microfarad, and that's 12 volts. Okay, so we solve for part A. Nice. Now, in part B, we're asked to find the charge of each capacitor. So this is where I'm going to draw you guys a nice little table here. They'll make things nice that Oscar brought up. So we have capacitors. I'm going to write cap, and we're going to draw a little thing like this. We have resistors. I'm going to write resistors. And we have situations when they are in series, or parallel. Okay, so resistors in series, when you combine them all, so R, I'm gonna write REQ, is just you're gonna sum them up, right? So it's equal to the sum. So how do you, that's like that, sigma R, and you just add them all up. Versus in parallel, 1 over REQ, that's equal to that sigma. Technically, it's like N over, and then I equals 1 underneath, but let's not complicate that. It's unnecessary. And then, oh, wait, this is backwards. I was like, wait a minute. That's for resistors. Okay, now for capacitors, in series, 1 over CEQ is equal to the sum of 1 over C, and you just add them all up. Okay, and then for the capacitors in parallel, that's just going to be, you just add them all up. Come on, guys, why don't no one tell me? I was writing it in the wrong spots. Okay, so that's how you do that. But now, kind of importantly to note is capacitors that are in series have the same Q, the same charge. Oh my gosh, why do I keep doing this? So capacitors that are in series have the same charge versus resistors that are in series have the same current. So same I, okay? And now shared between capacitors and resistors is the same voltage when they're in parallel. Okay, so that's a nice little summary of things. Oh, they said this is on the equation sheet, so.
What it only teaches how to find the total resistance and capacitance, but not the
not like the rule. Okay, so remember that then. So now we can, knowing this, we now have like the nice little way to remember how to solve for this kind of scenario. So the first thing we're going to want to solve for is QEQ, right? Because we don't know anything else. We need to always start with QEQ because all we know is CEQ times V is equal to QEQ. We know what the V is, so we know it's 2.5 times 12, and this comes out to be equal to 30 microcoulombs. So QEQ is equal to 30 microcoulombs. Well, looking at this position right here, so we're going to say this is QEQ. That capacitor is made up of 3 capacitors that are all in series. So capacitors in series all have the same charge. So therefore, QEQ, QEQ, QEQ. Oh, someone's unmuted. So therefore, we now know the charge at Q1 is equal to 30 microcoulombs. Okay. Now the next thing we need to do is to solve for the charge of these capacitors, right? And remember, those capacitors live within this one. But how can we do that? Well, we know that capacitors that are in parallel have the same voltage. So all we need to do is find the voltage drop across each one. I'll say that's V, and this is V prime. Okay? So, well, actually, they're going to be equal to each other, but that doesn't undermine the point, the fact that you would have to solve for both of them. If it were, like, it happened to that they're equal, but that's not always the case. So Q EQ is equal to C, and then what's the capacitance there? Well, it's actually the 10 microfarad capacitance, right? Remember, 10 doesn't really exist, but for our cases it does. And then V, which is equal to where am I missing? Oh, we have to solve for V, yeah. And then for the other guy, and it's also the C of the 10, V prime. So you solve for V, solve for V prime, and they both equal 3. Okay? So now we know that across each of these capacitors is V, 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 and this one's V prime and V prime, right? It's made up of all those guys. So now all you need to do for each one is, Q2, what's the capacitance of Q2 is equal to 4. And then what's the voltage there? Well, they're all 3. So 3. So then Q2 is equal to 12 microcoulomb. Okay, bam. And the next one, Q2. Q3, that's going to be Q3 is equal to C3 times V. So 4 times 3 is equal to 12. So 12. Okay, Q4, I'll just tell you, is equal to 6. Q5 is equal to 18. And then Q6 is equal to 12. All right, any questions? Gosh. So question 5, we have 4 long straight wires. Each are perpendicular to the page, and they're arranged on the corners of a square. So we're told that the current I1 is the value is 2 amps, and it's going out of the page. So let me draw. So Q5, here's a situation with a square, and something like this, right? And actually, this is a bad question because otherwise they would have to give you the drawing on this kind of thing. All right. So I'll just draw it out instead of having to read everything. They would totally give you the drawing for this kind of stuff. I1 is equal to 2 amps. 2 is equal to 1 amp. Okay. And then center is point P, this. Okay. And we're told that this is 1 meter. This is 1 meter. And we want to determine the net magnetic field at point P, which is located in the center of the square. Okay. So we first need to figure out a few things, which is the distance between each wire and that point P. So we'll right here, right? And we'll just call that R. And you can quickly solve for R using Pythag, and it equals, and R is equal to 0.71 meters. Okay. And the next thing we need to do is determine the direction of each of our B fields, right? So you guys know what I like to do with, like, I do my thumb, put my this part on the shortest distance between them, and I let my fingers point the direction it would be. And remember that it's going to be like going like a circle like this that will always be perpendicular to the shortest distance between them. So shortest distance between them is this guy right here. Perpendicular means 90 degrees, so I can either point this way or this way. But because my fingers curl and they're pointing like, upwards, I know that it's going to be this one right here. And I'll call that B1. Looking at I2, kind of the same logic, except now it's going to be going this way. I3, this way. And then, I4 is going up this way. Okay. Well, we need to break this into its components. So I'm going to draw a little line here and have X and Y components. There's going to be, this is the angle theta right here. And theta is going to be equal to you can just use tan 0.5 or 0.5. So 1 is equal to 45 degrees. Okay. And our X and Y components. Let's first start with B2 and B4. Well, they're both going the same way. Well, actually, I won't use this because I use that for my distance. Like this, this. This is B2 sine theta plus B4 sine theta. And then this is B2 cosine theta plus B4 cosine theta. Okay. And then over here, oh gosh. I have B1 cosine theta plus B3 cosine theta, B1 sine theta plus B3 sine theta. Okay, I have all my little components. I drew it all out. Solve for B net. B net is equal to B net x squared plus B net y squared, square root that whole business. Let's start by solving for B net x. Let's look at everything that is in the x direction, which is going to be B2 cosine theta plus B4 cosine theta minus B1 cosine theta minus B3 cosine theta. Okay. And if you got to this point, you know how to do the rest. All you gotta do is plug in all you express what B is equal to and factor. I recommend factoring everything out except for what you can't factor out, which is going to be the currents, because each current is different, but everything else is constant. So you do that, and what you end up with is B net x. Does anybody need to see me do that? Or are we good skipping that? Okay. So B net x is equal to minus 0.000. Sorry, I don't mean to rush, but also I do mean to rush because we do have a lot. And then B net y. Everything's pointing upwards with respect to B net y. So I'll just kind of skip writing what everything is and write what it would look like if you did this part and then factored everything out. It would be mu naught over the 2 pi r sine theta, and then I2 plus I4 plus I1 plus I3, and then that whole business is equal to 0.000012 t. Okay. And because our x is negative, it's going to be pointing this way. Our y is positive, pointing this way. And then this is B net. This is going to be the angle of interest. And I predict you guys know how to handle that part. Right? This should all be familiar. And then B net is equal to 0.000000126 t. And alpha is equal to 71.6 degrees above minus x axis. Okay. So sorry, we are going kind of quick, but this is the important part. All right, any questions on that? So here we have a situation where we have this slide wire generator, and there's this rod which has a length L, and it's moving towards the right, and it's immersed in a constant uniform magnetic field that's going into the page, but that has a strength of 0.5. The wire is pulled to the right with a constant velocity of 2 meters per second. So we'll say V is equal to 2 meters per second. Okay. And then the circuit, an EMF is induced in the current flow of the circuit. And that makes sense, right? Because we have a ring that's expanding. The circuit has a total resistance of 2 ohms. And in what direction does the current flow in the circuit, clockwise or counterclockwise? It's part A. You raising your hand? Oh, no. Anybody want to take a shot? Question, let's see, answer in the chat. Counterclockwise, nice, yes. So basically what Lenz's law tells us is when a conductor has a changing magnetic field, there's an electric current that is induced within the conductor, right? And then the direction of this current opposes the change in the field that induced it. So it's basically like something that's, you can think about it like in the terms of the conservation of energy, where if you have, more B, in this case, we're going to have more of the B field going into this ring as this rod goes this way. And then to oppose that change, there's going to need to be more going out of it, right? And a condition when you're going out, when you're going to have more going out, that's always going to be a counterclockwise induced current. So A, counterclockwise. And I think I made a table where I summarized, like, if it's going to be increased going in, you have to increase going out, and that's going to be counterclockwise, and then the other three scenarios. Okay. Part B here, what is the magnitude of the induced EMF? That's just an equation we'll use. And because we have this kind of a special version of the equation, and it cleans it up a little bit. Whenever you have a rectangle or a squirrel, I said that because I have a friend who's taking like the chasing squirrels class. Yeah. And like they have like a radar gun and they chase the squirrels because they wear necklaces that have like a little chip in it. You guys have never seen that before? Yeah, they have necklaces. Yeah, I think it's mammalogy, I say. Yeah. Anyway, I like took a picture of a squirrel and sent it to her, and I was like, "This is for your final." And so that's why squirrels are on my mind. So if you have a rectangle or square moving through a region that has a magnetic field, you can use this equation, and that equation will save you a lot of time because now all you have to do is plug in B, which is known, the length, which is known, and the velocity at which it's moving, which is given. So this whole thing goes 0.5. Okay. And then what is the current in the circuit? Well, we can solve for I induced. We think about it in terms of Ohm's law as equal to the V, or in this case, the induced EMF, divided by the total resistance, right? So instead of writing I equals V over R, we're going to write the induced current is equal to the induced EMF over the total resistance. And that equals 0.25 amps. Okay. And then part D, what force must be applied so that the rod maintains a constant velocity, right? So we want to have an acceleration equal to 0 in the x direction. So what we're going to have is an opposing force, we'll call FB, is going to be equal to F, right? Such that they're equal. So this is FB. All right. And what's that force equal to? Well, we don't know, right? But we do know how to solve for it because we know what FB is equal to, which is equal to I induced L, and it's a cross product with B, but we don't need to worry about that because it seems like there's never been a time where the angle wasn't 90. Well, cross product, it's sine of the angle between them, and it's equal to 90 degrees in most cases, but anyway. So that's going to be equal to 0.25 times L, which they tell us is equal to 0.5 times 0.5, which is B, and F is going to be equal to 0.0625 newtons, and that F is going to be going rightwards, right? Oh, so FB is the direction of the magnetic force given the situation of the question, and to maintain that constant velocity of moving 2 meters per second to the right, you'll need to have F there. So rightwards. Okay. All right, so let's just take a timeout real quick because we're at an hour. So here we have a triangle where we have light enter at 45 degrees. Remember that your angle that you're going to plug into Snell's law is always the one that is touching the normal, where the normal is perpendicular to the surface that the light enters. So you solve for theta 2 using Snell's law. And then because it's a right angle here, you can solve for theta 3. And because that establishes a triangle, you can subtract theta 3 and 60 from 180 to get theta 4, which is right here. And again, because you have a right angle here, 90 minus that theta 4 is going to be equal to that theta 5, which is the angle touching the normal, which is what you plug into Snell's law, and you can solve for the exit angle. Okay. Any questions on that? Okay, so here we have a double lens situation, and I think that they said that it would be lenses, not mirrors. Yes, so forget everything you know about mirrors. I'm joking. I'm joking. So question 8, double lens situation where we have the focal length of the first one. Okay, so we have two lenses. Focal length, the first one is 20 centimeters, and then the second one is minus 10 centimeters. They're placed 25 centimeters apart. And then an object is placed 60 centimeters in front of the converging lens. What is the position and magnification of the final image formed? Okay, so I was kind of being helpful there. I told you what came first and what came second. But what this requires you to understand is the sign of the focal length and if it's converging or diverging. Remember, positive focal length, converging, negative, diverging. They tell us that the object is placed in front of the converging lens, F1. So that means when we draw this guy out, we'll say this is our object here, converging lens, diverging lens, this. And we know that it's 60 centimeters. And F1 is equal to 20 centimeters. F2 is equal to minus 10 centimeters. Okay. And we're told that from here to here is 25 centimeters. And we want to determine the final image location. Okay. So we're going to use our lens maker's equation to first solve for the distance of image 1, like where the image 1 will be projected. So in part 1 here, we'll say 1 over F1 is equal to 1 over D1 plus 1 over DI1. Okay. All right, solve for DI1, plug everything in, and you can solve in terms of centimeters, which is I always like about these kind of questions, is equal to 30 centimeters. Okay, so where's 30 centimeters though, right? We know it's positive, so it's on this side of the, it's real, right? So that means it's behind, DI1 is positive, so it's real. That means the image is behind the lens. So it's going to be somewhere over here, but this is 25 centimeters. So it's actually right over here. So I'll say this is image 1 right here, image 1. Okay. And then we can now solve for the DI2 because we have, because the, the image produced by lens 1 is the object of lens 2, right? So for part 2, 1 over F2 is equal to 1 over DO2 plus 1 over DI2, okay? We now plug everything in, 1 over minus 10, which is equal to 1 over 5, because from here to here is equal to 5 centimeters. But because we're on the opposite side of the lens, we're on this side of the lens, we plug in a negative 5, okay? And then plus 1 over DI2, okay? DI2 is equal to 10 centimeters, and behind, it's positive again, so that means we're gonna be behind the diverging lens, so it'd be somewhere like right here. So 10 centimeters. And then we were also asked, what's the magnification of the final image? Well, magnification total, so I'll just call that part A, where we solve for where the image will be finally. And then part B, the total magnification. We'll say M total is equal to M1 times M2. And now don't forget that we actually have a negative sign embedded in this equation, so that needs to be acknowledged. And then 2, okay? So when we plug everything in, that'll be minus 30 over the distance was 60, and then minus 10 over minus 5. These negatives cancel out. It's going to come out as a negative 1. Okay. Pause real quick. So now we have these pesky single double slit diffraction equations. So in question 9, we're asked how wide is the central diffraction peak on a screen that is 2.3 meters behind a super small slit and illuminated by a light who has a wavelength of 558 nanometers. So we kind of have two different scenarios where there's a single slit and double slit type question, right? So with respect to the single slit, the intensity is gonna be this big curve, right? It's gonna look something like that. Versus in the double slit, within, like, it'll be something like this. And within this, there's gonna be all these many peaks with one really tall one in the middle, right? Okay. And between those bright fringes on either side of the central bright are these dimmer ones, and they get progressively closer together. And then there's going to be a dark fringe in like littered between them. And I have this whole business about when you have like the max situation, which means you're solving for a bright is equal to d sine theta m plus 1/2 lambda. And what's that deal with that 1/2? Well, basically with the, I don't even know if it's worth explaining, but yeah, actually, I'm not going to even go there. It's a calculation modification because on both sides, you kind of like you ignore the first one. So you need to split that in half and then you add 1/2 because you're skipping that half. So you start counting on the next. Yeah, exactly. Yeah. Okay. But I don't know. It's no point in overcomplicating. So Q9, we're told that we have a single slit, okay? And we're looking at the central diffraction peak on either side, okay? So on either side, that means we're gonna be looking at the dark region. So if we draw this out, it'll be something like this, okay? And we know that from here to here is that width of the slit, which is whatever it was, super small, 3.48 millimeters. Okay. And then from the central position to over here is going to be some distance L. And the light kind of goes like this on both sides. Okay. So then we have an angle theta right here. And at the center, we're going to have that bright, but that's going to be like the order number there is 0, right? Because it's single. So when we draw out what the curve kind of looks like, it's going to look like this. Something like that. Pretty bad, but you get what I mean. Where that first one right here, this is going to be the bright, and this is going to be the first order dark. And I'll call this one -1 because it's going to be on the bottom side like this, right? And what we're solving for is the distance between those two darks right there, right? Those dark fringes. So what's that equal to? Well, we'll first call this x, and that means from here to here is equal to 2x. Okay, so the fringe pattern that is formed by a single slit consists of alternating bright and dark, right? So we're looking between those dark, that means this is going to be equal to 2x between them. Our equation in this scenario is d sine theta equals m lambda. Okay, we can rearrange to solve for theta. Like this, sine inverse m lambda d, where m is equal to 1. And your angle is going to be pretty small. Like in these kind of questions, if your angle comes out big, unless it's a weird question, I would say, that means you probably messed up. And the next thing we're going to be able to do now is knowing theta and knowing from here to here is also x, we can use a tan function to solve for what x is equal to, because we know the distance that this opening is from the screen. So we can solve this guy out. Tan theta is equal to x over L. X is going to be equal to 2.3 tan, and then the angle we just found. Okay, and then you can multiply that whole thing by 2 to solve for 2x, which is what we're looking for. And then that whole thing is going to be equal to 0.0738 meters. Okay. All right, any questions on that? So we have light of wavelength 541 nanometers is sent through 2 slits, double slit, and is projected on a screen 4 meters away. The slit centers are 3.2 micrometers apart. What are the locations of the first two double slit maxima. Okay, so we know it's double slit, and we also know it's bright because we're going to be looking to the right of the central maxima, right? The maxima to the right of the central maxima. So the peaks to the right of the central peak. So let's draw this out. Okay. Theta. From here to here, we'll call x1. From here to here, we'll call x2. And which equation we're going to use? D sine theta. And lambda. So the first thing, we need to solve for theta 1, right? So theta 1, this is basically like I'm doing what we did last time. Theta 1 is equal to sine inverse m1 lambda over d. Now, could someone tell me what I'm going to be plugging in for m? Remember, this is a double slit equation here. So my first bright to the first bright will be equal to 1, right? So don't get that mixed up between the single and the double scenarios. Because remember, the first one for the single slit will be a dark. Okay. And then tan theta 1 is going to be equal to x1 over L. And they tell us what L is equal to. And they tell us what L is equal to. So therefore, we can solve for x1 as equal to 4 tan 2.35, and x1 is equal to 0.164 meters. And then for solving for x2, you know, it's going to be really the same setup here. So I'll just kind of say a dot, 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 and you get theta 2, which is 4.7 degrees, and then solve for x2 in the same way. X2 is equal to 0.329. And the difference is the order number is going to be 2 there because we're dealing with the next one up. And it's a double slit bright. Okay, so any questions on that?
So for that single slit,
so this is going to be, you know, we have this wedge situation. There's something in between it. That's thin film interference through and through. Like if you see that, think thin film. So basically, light is going to be reflected from the top and the bottom. And this can result in either constructive or destructive interference, which is going to be a bright or dark fringe, right? So what's the difference between constructive and destructive? You can think about it like when it constructs, it's like the two amplitudes will add or become bigger. Whereas destructive, they cancel each other out. And my fun fact about that is, you know, when you wear sound canceling headphones, you listen very closely when noise is happening, it emits like this high frequency sound. And that high frequency sound is destructive to the sound that's around you. So it actually cancels that sound. That's how it works, which is pretty neat, huh? You guys are in, is that neat or what? I think when I found that out, I was like, oh, yeah. Okay, so depending on that interference pattern, it can be bright or dark, right? So to determine whether it's going to be constructive or destructive, you need to look at the phase difference between the reflected waves. And when two waves have a phase difference of 0 or an integer, a multiple of the wavelength, they interfere constructively, and that creates the bright fringe, right? So like in this case, I think we're looking for the bright. Yeah, we're looking for the bright band. And conversely, when the two waves have a phase angle difference of half a wavelength or an odd multiple of the wavelength, they interfere destructively and they create the dark fringe. Okay, so that's what I'm saying. Like if you don't know if the first one's going to be a phase thing, you can be solving this thing all wrong. Okay, so in this case, let's draw out what we have. So we have these two pieces of glass, and they're separated on the rightmost side by this block. And the interior has some material that has an index of refraction of 1.15. And light normally is incident on it from above. At what X value is the first bright fringe for red light of wavelength 600 nanometers? Okay, so these ones are always a little bit remember these ones are always confusing. So let's take our time. So it's question 11. We have something that looks like this. And here we have n is equal to 1.45. N is equal to 1.15. N is equal to 1.45. Okay. And from here, here, it's a distance L. They tell us the height of that block that's on that side. And am I missing something? Oh yeah, we're looking for X, which is going to be where that first bright happens here. Okay, so we have our light. It's going to enter the system. It goes like this. And there's going to be some diffraction that happens here, but also it's going to continue down here. Now, oh, sorry, that's kind of bad. All right, this is a horrible drawing, but it still gets the point across. So tell me now, how many phase changes are there and where are they? Yeah.
That first one, maybe, this one, it's the glass from above.
All right, I didn't tell. So on this one, that was kind of my trick there. We're not working with air. There's going to be nothing. So imagine we're in a vacuum. Yeah.
What are the steps are gonna be at the,
Here?
no,
Here?
yeah,
Yes. So we have one phase change. So I'm going to say times 1 pi shift, or it's called a pi shift also. Whatever you want. Okay. So we're looking at the first one, and actually this drawing is way worse than I thought because it would actually look something like this, actually. We're asked to solve for the first, one sec. Yes. Yeah, Maya, you're right. The first bright band. So bright band, we're going to be using the equation 2D is going to be equal to m plus 1/2 because that bright. And then the lambda of the substance, right? Can't forget that. We can't use the wavelength that it is in air. We need to use the lambda of the substance. And I'll say over here where lambda substance is going to be equal to the lambda in air or in a vacuum, and then divided by its index of refraction. So in this case, that's going to be that goo or whatever that's inside. And okay, we're done there. So what is the order number here? Oh, and actually we should let me put this down here actually, because I'm gonna rewrite the whole thing. So we're gonna divide by 2, and we're also going to change that lambda substance to what it actually is. So D is going to be equal to m plus 1/2, and then the wavelength 600, right? 600 times 10 to the minus 9 divided by 2 because we had a 2 on the other side, times the index of refraction of that goo on the inside is 1.15. So I gave you everything, but what's m? For the first one, first bright, it's going to be equal to 0. And that's why with this scenario, we add the 1/2, right? Because otherwise it would be multiplying by 0. So that's what I mean when I said we have those conditions for when it's going to be constructive, or it can have or destructive, right? And I did a worksheet where I kind of went in depth, and I think I wrote it out on that. So check that worksheet out. So m is equal to, I'll just rewrite that, it is equal to 0 here. So D is going to be equal to 1.304 times 10 to the minus 7 meters. Okay, solve for D. I didn't even tell you what D was. But D is the distance the light goes from this position here. Should actually be a vertical line. So right there, that's what D is. That's going to be where the first time you're going to see the bright band. That's what D1 is, D1. Right? So then for D2, you would then plug m equals 1, et cetera, et cetera. But for the first one, we plug in 0. So now we have what D is equal to, which is not what we're looking for, but we can set up a ratio because this is the wrong symbol. We can set up a ratio as D1 over X1 is going to be equal to H over L. And that's why I like this question, because it makes you remember the fact that this triangle here and this triangle here, you can set up a ratio between them to solve for the unknown, which in this case is x1. So solve for x1, which is going to be equal to d1 times L over the height. And x1 equals 3.17 times 10 to the minus 4 meters. All right, let me pause real quick. So for question 12, we want to calculate the kinetic energy of a proton that's traveling at a certain velocity. So Q12 is we're looking for what KE is equal to. Jeez. So KE, and what's that going to be equal to is going to be equal to the total energy, which is mc squared over the square root of 1 minus v squared over c squared minus mc squared. Okay, so in the middle, this part right here, we have total energy. On the right here, we have the rest mass energy. And this is really powerful and subtle thing. Like, this is a cheeseball question where all you have to do is plug in and solve, but the concepts really make it powerful. So when we're looking for kinetic energy, we're just looking for it in motion, right? So we have this total energy subtracted by the rest mass energy, which is equal to the energy that any particle has, right? Through the equation E equals mc squared, energy and mass are interchangeable. So with this subtraction, all we're left with is the kinetic energy. So KE is equal to 6.313 times 10 to the minus 11 joules. Okay. Question 13. We're at time, dude. Maybe I'll post my solutions for the rest. I can do question 13 really quick. All right. So question 13 is a combination of time dilation and the Lorentz transformation. So a common question, okay, I'll give you so Bob and Alice are moving. They're both inertial observers, and they're on the X plane together. Bob measures a time of 30 seconds on his watch. Alice is 45. Determine the speed V. That's what we're doing part A. And then we're going to see some Lorentz transformation stuff in part 2. So really quickly, I want to show you this table that I made that I used during my SI sessions, just because it really makes things a lot easier for these kind of questions. Okay, so within relativistic conditions, we either have a time dilation or a length contraction. Okay, so this is a table that's always true. You have your stationary frame and you have your moving frame. The stationary frame, by definition, sees the event happening more slowly. Time is dilated. They will also, or I'm sorry, and then that's delta t. I call it delta t, but I know they use like prime and whatever. To me, this is easier. And the moving frame, delta t naught, sees the normal time. The normal time is like Felix the cat has a lifespan of 9 years. Remember that question? 9 years is the normal time. Okay. Delta t will always be smaller than delta t naught, right? And that makes sense, right? Time is dilated. It takes more time for the same event to happen. Alternatively, with length contraction, the stationary frame observes the normal distance, L, and the moving frame experiences L naught, and the moving frame has L, which is the length contraction. Thereby, L is always smaller than L naught. So sometimes when you're given a question that has 2 times, what goes what? What's the stationary frame? What's the moving frame? Remember that this is always true. Okay? So that's kind of nice. And with respect to the question we're about to solve, delta t is going to be equal to delta t naught divided by 1 minus v over c squared square root. What goes where? Well, I already told you that delta t naught is always going to be, or delta t is always going to be bigger than delta t naught. So that means we get the 30 in the numerator, and then, whatever goes in the denominator, and then 45 here, and then solve for v is equal to 0.745c. Another question is, when do I use relativistic conditions? If you're at least 1/10 the speed of light, use relativistic conditions. Now, in part B, this is the new stuff, or at least the harder stuff. Alice sees 2 flashes, and they occur at x position 40 meters and t position, or in time 1, 10 nanoseconds. And the second one happens at x position 6 meters, and the time of that one is 45 nanoseconds. According to Bob, who what is the spatial separation for those two flashes. So now whenever you see me write prime, that means with respect to Bob. So to solve for this, we need to use a Lorentz transformation. And a Lorentz transformation is the relationship between two different coordinate frames, Bob and Alice, that move at a constant velocity and are relative to each other, right? You can imagine they're moving together like this. And Amelia, remember, I think you brought up something. You're like, hey, why is it negative for part 3? And I think what you said was right. After I went home, I thought about that. So yeah, anyway, we'll get there. But I just remember that. So now for part 2, let's calculate x1 prime and x2 prime. And to do that, you just need to use the equation x prime is equal to x minus v over t divided by the square root 1 minus v squared over c squared. Okay, so you can solve for x1 prime just by plugging x1, x1, right? Because remember, this can be 1 or 2. And this is 1 or 2. And they gave us what 1 and 2 for this x are in the question. So all you have to do is plug in the appropriate one and you'll solve. So let me write it out for the first one. Sorry, guys, I know I'm flying right now, but. Okay, and that is equal to 56.6 meters. And please note that instead of writing this whole expression down here, I solved it out. It's equal to, and I wrote it horribly. It's equal to 0.667, right? And that's because this little downstairs part, you're gonna need to solve 600 times. So rather than plugging it in every single time, solve it once, plug it in and then just use the same thing. Okay, and then let's do the same thing for the next one. Okay, and then you find the difference between them. And that's going to be equal to 18.3 meters. Okay. And then in part B or part C, we're asked, what's the temporal separation between these two flashes? So this is part C. And we're going to have a similar expression. Oops. Like this. Okay. And all you have to do is plug in kind of in a similar route as done before, and you'll solve for t1 prime, which is equal to minus 1.34 times 10 to the minus 7 seconds. And then t2 prime is equal to minus 1.55 times 10 to the minus 7 seconds. And then delta t prime is equal to minus 0.21 times 10 to the minus 7 seconds. And Amelia, do you want to say it or should I say it?
You can probably say it better.
Go for it.
Okay, so Bob and Alice see the events happening in different orders, and that's the thing that screwed with my head when I first saw this problem. Because T2 minus T1 is negative for one observer and positive for the other.
So that means the order in which they see the events are flipped. All right. You have a question?
Oh, no.
Or just patting your head? Okay. That's it. Take it, you're scooping it in. All right, that's it. I'll post my solutions for the next 2 and I'll write an explanation for them. Thanks, guys, and good luck.